Thank you for the introduction, and thank you all very much for giving me the opportunity to come and talk about my thesis work. I'm in the Department of Chemistry, so my talk might be a little bit different. I'm going to try to give some good background at the beginning of it, but I'd like to start by acknowledging all of those at Berkeley who've got me where I'm at. First and foremost, the UC Berkeley, Lawrence Berkeley National Laboratory Heavy Element Nuclear and Radiochemistry group. This is the group that I've been doing my PhD work in, and I'd like to specifically point out our principal investigator, Hainonichi, who's here in the audience and has been very, very supportive. I'd also like to mention some of the undergraduates and postdocs I've worked with, and the Lawrence Berkeley Lab 88-inch cyclotron staff and postdocs and scientists have been very helpful, and the experiments that I've done really couldn't have happened without any of them. And the various funding sources, mostly from the Department of Energy. The NNSA has been very good to me and shown me support through both the Stewardship Science Academic Alliances grant and through this great fellowship that I've had here. And I'd also like to specifically mention CREL for doing a great job of administering the fellowship. You've made it very, very easy for me to do some great science. So all good nuclear chemistry talk should start with a periodic table. So here's mine. The elements that I'm going to be talking about in our talk are mostly down here at the bottom. Here I have plutonium highlighted. My experiments used an isotope of plutonium as its target material, which I irradiated with protons to make an interesting isotope of americium, and with calcium-48 ions to make an interesting isotope of the yet unnamed element 114 and its radioactive decay daughters, copernicium, darmstadtium, hassium, seaborgium, and rutherfordium. To give a brief overview, I'll start with an introduction to these type of low-energy nuclear reaction experiments. I'll talk specifically about the production of our targets that we use for the irradiations, and then I'll talk about the two science goals that we did with them, making americium-240 and making this new isotope of element 114. So, at their most base level, these low-energy nuclear reaction studies first involve a target. This target's generally a thin metal foil or maybe an electrode deposition spot on a metal foil. We then use a particle accelerator to accelerate ions to energies in the several to 20-some MeV per nucleon. This irradiation will then rarely fuse the projectile and the target together, forming a compound nucleus, which is an excited nuclear state. It de-excites by giving off various radiations and particles sometimes, giving us the product of our nuclear reaction. If we're concerned with the production rate of our product, we have to look at a variety of things. First, the number of target atoms and the intensity at which we're bombarding with the projectiles, but also this term, which we represent as sigma, which we call the cross-section. And this value is essentially the probability for this nuclear reaction to happen. And it's very dependent on projectile, on the target, and on the energy of the projectile. And this value is measured in units of area. Seems kind of strange to measure probability in units of area, but one way that you might think about this is playing basketball. If you're trying to throw the basketball through the hoop, the probability that you're going to get it through the hoop is largely dependent on how big the hoop is. With those small basketball hoops, it'd be very hard for me to get it through. But if I was trying to throw the basketball into a swimming pool, which has a much larger area, quite a bit easier. So we measure cross-sections in unit of area. We use this term a barn, which is very, very small when you think about swimming pools. The targets that we used for these irradiations were something very, very special in themselves. So I say we use plutonium targets, but when most people think of plutonium, they think of plutonium-239. That's the isotope of plutonium that's used in fission reactors in nuclear weapons. And the plutonium that we used was not that. We used plutonium-242, which is an isotope of plutonium with 3 more neutrons. And to make plutonium-242, you keep plutonium in a nuclear reactor longer, so it captures more neutrons, and then you have to do some sort of an isotopic separation to isolate this plutonium-242. And because this type of isotopic enrichment is very difficult to do. Highly enriched sources of neutron-rich plutonium isotopes are very, very precious. Very rare. They were only made at one point, or very few points in the history of the DOE complex. We were very fortunate to have a sample that was produced as part of the Transuranium Isotope project from Oak Ridge National Laboratory that is very highly enriched in plutonium-242. This makes it very well suited for such nuclear reaction studies because we want to have isotopically pure of a target as possible. However, it had been a very long time since this sample had been chemically purified, and so it had quite a bit of americium growth in from the radioactive decay of the plutonium-241, which was in it. Plutonium-241 has only a 15-year half-life, so this 30-year-old sample had quite a bit of that decay into americium. And so we had to start all of this work by doing some wet lab experiments where we dissolved and purified using this ion exchange column 150 milligrams of the plutonium. So this is wet lab work, which we have to do in glove boxes to prevent contamination, and is really quite a large project because of the very tricky chemistry of plutonium. The separation itself isn't so bad. We can do it with a rather straightforward anion exchange column, but the producing plutonium targets is quite a tricky task. We used electrodeposition. Here, this is one of the electrodeposition cells we used. I have a schematic here. The way electrodeposition works is we prepare carefully our plutonium sample in an isopropanol solution. We then put the isopropanol solution for this cell down a chimney of this electrodeposition cell. We have our target backing, which is a 2 micrometer thick, very thin titanium metal foil clamped to the base. We also have an anode made from palladium. We then charge the palladium anode with a positive current, that then, or positive voltage that attracts the anions in the solution, and the cations, which are the plutonium cations, are deposited onto our metal foil. Here you can see a photo. This is a 7-millimeter circle plutonium deposition spot. This yellowish green color is the plutonium. You can see the darker titanium metal and a thicker aluminum foil for support, because when you're handling these thin foils in a glove box through 3 pairs of gloves, you need something to help you hold on to the thin foils. These circular targets we used for half of the irradiations. Half of the irradiations we wanted to irradiate a larger diameter target. This circular target was made up of 4 banana-shaped target segments. We used this larger electrodeposition cell that works largely in the same way except turned on its side. And here you can see a photo of 2 irradiated targets and 2 not yet irradiated targets. So this production of these targets was really a very difficult task. It took me about the first 2 years of my PhD to do the wet lab chemistry. I learned a lot of plutonium chemistry, americium chemistry, radiochemical separation techniques, and Berkeley is a really unique place that still has this sort of a capability to be able to teach students in actinide radiochemistry. So this was my overview and my plug about our targets. So let's move into some of the exciting science that I did with these targets. So I'll first talk about americium-240. So what I have up here is a section of the chart of the nuclides. Each one of these squares is a different isotope of an element which goes across on the rows. So here you see plutonium isotopes. Here you see americium isotopes and curium isotopes. They're colored based on their radioactive decay properties. Here you can see the key for that. The isotope that I wanted to make with these plutonium-242 targets is americium-240. So you can see americium is more on the neutron-deficient edge of americium isotopes. It has only a 51-hour half-life, which makes it difficult to use as a excuse me, as a target itself for nuclear reaction studies. But so that may lead you to the question as to, okay, I know what americium is now. Why do we want to make it? Well, what we want to do in the long run is do this very difficult task of performing a neutron-induced fission cross-section measurement on americium-240. Why do we want to do that? Well, for a variety of goals that are important to the National Nuclear Security Administration. First, it has an important role in post-detonation nuclear forensics. So if there were a nuclear detonation and we were trying to gain information about it after the fact, the cross-sections on this isotope are important for us to be able to gain information from nuclear debris. Also, it's important for the science-based stockpile stewardship effort for us to be able to accurately predict and predict the efficacy of our nuclear deterrent. We need to have very accurate measurements of this value so that we can put them into simulation codes. It's also important for predictions of nuclear waste isotopics of the minor actinides, which is important for next generation nuclear powered. But to do such a measurement, the reason it hasn't been done in the past is frankly just because it's so difficult to do. As I mentioned, it has this 51-hour half-life, which makes making it in quantities large enough to do such a measurement very, very difficult. However, one of the best places where this measurement can be done is at the Los Alamos National Laboratory's Neutron Science Center. They have a lead slowing down spectrometer. This lead slowing down spectrometer is very well suited for doing neutron-induced fission measurements on very small amounts of very radioactive target materials. It's been shown in the past that they can do measurements on as little as 10 nanograms of actinides for this type of a measurement. And so when you have something that's hard to make, you need an instrument that can measure it on as little as possible. However, for americium-240, making a pure target in the 10 nanogram quantity is still very, very difficult. This is because americium-240 can't be produced in a nuclear fission reactor because it's neutron deficient. And all previously studied nuclear reactions for the production of americium-240 produce it in quantities that are just frankly too small to be able to use to make it for a lead slowing down spectrometer target. They have these cross sections of only 2 to 3 millibarns. Fortunately, there is another nuclear reaction that hadn't been explicitly measured in the literature, the proton bombarding of plutonium-242 at an energy that 3 neutrons were evaporated to make americium-240. This nuclear reaction had a high predicted cross-section through a Los Alamos code and also an old fusion evaporation code. It had a high, about 100 times larger cross-section than these others. However, it had never been experimentally measured for producing americium-240. So this was one of the main goals of my PhD work, is to experimentally measure this americium-240 production cross-section to verify that it would be a suitable reaction to produce it in the quantities to do this neutron-induced fission measurement that is our end goal. So here I have my equation for cross-section again in terms of producing americium-240. How do we do these experiments to measure sigma? Well, first we take a target with a known thickness of plutonium-242. This is the first 2 years of my work is producing the plutonium targets. And then we measured their thickness using a simple alpha counter. We then took these targets, and this gives us our thickness of our plutonium-242 target. We take these targets and irradiate them with the Lawrence Berkeley Lab 88-inch cyclotron with protons, with a measured intensity of protons to give us our intensity of the proton beam. The decay of americium-240 has been well studied, and so we know this decay rate. And after the irradiation, we separate our foils and count them using a high-purity germanium gamma ray counter and look for the 2 high-energy, high-intensity gamma rays that are given off with the decay of americium-240. We then count it over a month period of time and watch the americium-240 decay, and that will be back extrapolated to get our americium activity that we produced at the end of our bombardment. Fairly straightforward procedure. Once we have our targets, here I have a photo of them again. We wrap them in an aluminum containment foil and clamped them to a water-cooled aluminum block, which we put at the end of a beamline at the 88-inch cyclotron at Berkeley. We then irradiated it with protons and measured the proton dose. We also, in this stack, had some proton monitor foils, which were thin foils with well-known proton-induced nuclear reaction cross-sections, making a very easily measured isotope. So we had several ways of measuring our proton current. And we performed 5 such irradiations in Berkeley over 32 hours total of beam time at 4 different proton energies. And the plutonium foils that we get out, or the plutonium on titanium foils, once we count them in a gamma spectra, look largely like this. We have some background, but then very distinct peaks coming off the top of it. Those distinct peaks are coming from the gamma rays that are emitted from the radioactive decay of all of the isotopes produced in the irradiation. You can see the peaks are identified from various proton-induced reactions. You can see here I have my americium-240 peak and another one here. What we did then is we had an in-depth data analysis where we took a month's worth of 10-minute counts, looking like this isn't a 10-minute count, but a month's worth of 10-minute spectra like this, and did some elaborate subtractions of scanning of co-energetic peaks and subtraction of the background, and we're able to extrapolate out our nice americium-240 decay to give us our end of bombardment americium-240 activity. So the cross-sections that we measured, while they are lower than the predictions, they are about 40 millibarns. And while these are less than these predictions made, they still remain to be the most promising heavy ion reactions for producing americium-240 for a lead slowing down spectrometer measurement. And with these cross-sections of about 40 millibarns, what we plan to do next is we are planning to do a large-scale irradiation to produce americium-240 for a lead slowing down spectrometer measurement. This next step is a very difficult one. It takes a lot of collaborations and coordination with our collaborators at Los Alamos, because we'll need to first produce this much, which in itself will involve irradiating about 500 milligrams, about half a gram of plutonium-242 for 3 days with 5 microamps a beam. At these 40 millibarn cross-sections, that'll make about 100 nanograms of americium-240, which we'll then have to chemically purify from the target. We've also been working, I'm not going to discuss it here, but we've also been working on a chemical purification procedure, and then we'll have this all coordinated with the Los Alamos Neutron Science Center to do a lead slowing down spectrometer measurement quickly before this americium-240 decays. So this next step is a tremendous effort, and we are working, while my time is done here, we have an SSAA grant, which will continue working on this. And we have a collaboration meeting even just next week to go down to Los Alamos and discuss the next steps now that we have this cross-section measured and the separation procedure worked on. So this is the first part about the production of americium-240. What about our element 114 study? Well, let's take a step back to the periodic table. Element 114, the yet unnamed element 114, is one of what are dubbed the transactinide elements. Here the actinides end and the transactinides begin. Studies of the transactinide elements has been going on since about the late 60s, but in recent years, there's been really an explosion of growth in them. Element 113 through 118 have been claimed only in the last 10 years, and people are still working to be able to reproduce and confirm the experiments done. If we look at the chart of the nuclides to see the uppermost end, as opposed to the actinides that we were looking at before, I have the color, it color-coded again by decay. The uppermost neutron-rich end of these transactinide elements, you have these, which have all been produced first in about the last 10 years. They have all been produced 48 bombardments of actinide targets. Reports have been around since about 1999 of superheavy elements being produced this way from the Flarov Nuclear Laboratory in Dubna, Russia. However, they were only first independently confirmed in 2007, and then 2007 to confirm the element 112, copernicium, and 2009 we confirmed at Berkeley the production of element 114 in an experiment that I was able to collaborate, that I was a part of. But I'm going to be talking about 114 today. Here I have the 4 isotopes of element 114 that had been discovered before the work that we did recently at Berkeley. These 2 isotopes of the more neutron-poor were isotopes that were confirmed at Berkeley using the plutonium-242 targets that I discussed. But we wanted to do another experiment which took this a little bit step further. We wanted to make this new isotope of element 114 for a variety of reasons. One reason we wanted to make this more neutron-deficient isotope is because, based on some extrapolations of masses and predictions, it had a very long alpha-decay chain. When you're making these superheavy elements, if it alpha-decays a lot, that means you get to see a lot of elements, because once it spontaneously fissions, which is what this green is, then it splits in 2 and you no longer get to see superheavy elements. So the cross-sections predicted for this nuclear reaction were low, this 0.5 to 1.5 picobarns. We're now talking many orders of magnitude lower. Experiments like this are very difficult to do, and you end up producing only 1 or 2 elements in a week-long irradiation for isotopes, or 1 or 2 atoms of it in, say, a week-long irradiation. However, because it would be 6 new isotopes, and 5 of them we would be able to measure the alpha-decay energy. It was a very high discovery potential experiment. These 5 alpha-decay energies yield interesting information about superheavy element nuclear shell structure. This shell structure is the only thing holding these superheavy elements together, so it's of paramount importance to understand for their stability. And so the instrument that we use to do these irradiations is the Berkeley Gas-filled Separator. Because we're only making 1 atom a week or 1 atom a month, we need to have an instrument which can separate out that 1 atom from all of the other nuclear reaction products and all of the beam. The instrument that we use for that is the Berkeley Gas-filled Separator. Here in the schematic, we have the beam coming in from the left and going through this target chamber. As I mentioned before, the target chamber is this circular wheel which we make inside the laboratory and then put in a containment cassette which has a hole for the beam to go in and the nuclear reaction products to come out. We then seal it up and take it to the Berkeley Gas-filled Separator and put it inside this ventilated enclosure, which, due to regulatory reasons, because the way it's been commissioned, is not technically a glove box. So we call it a box with gloves. And we put it in the beam line here for irradiation at the front end of the Berkeley Gas-filled Separator. The BGS works with 3 large magnets which separate atoms based on their magnetic rigidities. Magnetic rigidity is the momentum over charge ratio. When we irradiate it with beam, the beam itself has a very low magnetic rigidity and take a sharp left turn going through. Other nuclear reaction products, such as transfer nuclear reaction products, do the same. We have 2 detectors here to monitor Rutherford scattered beam particles, giving us an accurate measurement of giving us an accurate measurement of the target thickness times the beam intensity. And then we run like this. And we keep running until we see something. What we're really looking for is we're looking down here at this focal detector area for a full fusion event which gets curved down based on its magnetic rigidity to our detector array. The detector array that we have is a silicon strip detector. We have many strips here which you can't see, which are position sensitive, allowing us to see exactly where in our detector we have an implantation of a recoiling atom. We also have perpendicular detectors of the same sort. This allows us to see various types of radioactive decays. Here I have a schematic of our focal plane detector. That's our element 114 recoiling into the detector. which can decay by various ways. It can give off a full energy alpha particle, which leaves all of its signal in the focal plane detector. It can alpha decay outward and hit one of these upstream detectors, leaving a signal in both of these, smaller here. It can go straight out and only see a signal in the focal plane. It can come out shallowly in the focal plane and not leave any signal in the focal plane, but only be in an upstream, or just leave no signal at all because it went out straight out the face of the detector. We're also looking for spontaneous fission decays, which are much higher in energy, around 200 MeV, and these give off 2 fission fragments in opposite directions, making them easier to detect because we have twice as many chances of seeing a signal. In the same way, we can see all of the signal on the focal plane. We can see only part of it, or here we can see it in both the focal plane and one of these upstream detectors. So because of this very versatile detector, we're very, very sensitive to see these type of decays. And what did we see in our experiment? Well, here I have these predicted decay properties of this new isotope and the decay properties of the one more neutron-rich. The results that we had were, we started running, and we saw great results, one very, very exciting result right away. This, you can see we had an implantation of about 16 MeV, followed by 5 different alpha decay events in this about 10 MeV range, and then followed by a high energy fission-like event. These are all well correlated in their positions and are quite similar to the predicted decay properties, with the exception of the spontaneous fission lifetime. We were very encouraged by this. This was exactly what we were looking for. We continued to run. It was right at the beginning of the experiment. Maybe the cross-section for producing it was much higher than we thought, but we just ended up getting lucky. So we continued to run, and later we only saw this more neutron-rich isotope, which matches the decay properties measured at both Dubna and Berkeley very well. So these great results we have here, we measured at the 50 MeV excitation energy. These solid points are Berkeley results. The open points are Dubna results. These curves are predictions from Zagorbayev. And you can see that the excitation functions match those pretty well, with the exception of maybe this 5N result, which is the most recent result that we had. And this showed that the cross-section was indeed possibly, agreeing with Aunt error bars here, larger than the predictions. And where does this all fit in on the chart of the nuclides? Well, these new isotopes are here on the neutron-deficient edge of these new isotopes. So I'd like to summarize again by throwing up this slide. These 2 interesting science areas, while different, both utilize these nuclear chemistry techniques to study 2 interesting scientific results. Thank you very much for your attention.